All right, welcome to a new day. Let's talk about a new topic. So we're just going to have time to get through the bitwise operators part today, but it's very exciting and very useful. All right, it's low-level stuff, so let's talk about it. I'm going to show you some things in C++ that let you operate on the individual bits of a number. We say that the operations are bitwise. They work on the bits, all right? So remember what that means? That's the individual ones and zeros in a binary number, okay? So like, you can go, there's a way to go and look and see if you have like an int. Go and look at this particular bit of that int and see if it's a 1 or a 0, okay? That's where we're going today. So we have to remember what binary looks like, definitely. Let's figure that out. And yeah, so a bitwise operator, first of all, it's just going to work on the individual bits of a number. You can like extract them, set them. Remember that a bit is 0 or a 1, right? That just stands for binary digit. And yeah, let's just have some examples. Let's remember binary. All right, so like 1011 is a binary number. What is that? Well, it's going to be 1 times 2 to the 0, right? 1 times 2 to the 0 plus another 1 times 2 to the 1 plus a 0 times 2 to the 2. It's the 4's place. Oh, sorry, that's supposed to be a 0. Excuse me. 0 times 2 squared. 2 squared plus a 1 times 2 cubed. Okay, and so if you do the math, that's going to be what? 248 plus 2 plus 1. That is the number 11 in decimal. All right, so that's something, hopefully, that is a review for you. And yeah, let's go further than that. And same idea with this one, like, okay, what is this one? 10011. That's going to be still the 1 times 2 to the 0 plus 1 times 2 to the first, but then a bunch of zeros, that would be the 2 squareds place, 2 cubes place, plus a 1 times 2 to the fourth. So like that one would be 16 plus 2 plus 1. That would make 19, okay? So that's important. Another thing that I'm not sure, I can't remember if I said it or not, if you have an int, right, an int is 32 bits long no matter what number is inside of it. It's always taking up the same amount of space. And so if you're storing a number 0 as an integer, it's going to hold 32 zeros because it's just the number 0, but it has to be 32 bits long. All right, 4 bytes total. So yeah, if you want to store the integer 0, it's going to be 32 zeros because every int is 32 bits. 32 zeros in the int 0. There are other types that hold whole numbers, but they might have different sizes, right? The char type technically holds whole numbers, but it's only 8 bits. So the number 0 as a char would only be 8 zeros. Okay, hope that makes sense. So yeah. I have also kind of swept something under the rug. I haven't told you how we store negative numbers. I've only told you how to make positive numbers, how to translate back. So integers can be negative, can't they? How do they do it? Let's figure that out. All right. Again, you only have 32 bits to work with in an int. How do we store negative numbers? All right. The answer is that we've given up some very large positive numbers. We've given up being able to represent them, and instead we gain negative numbers out of that deal. All right, so we've given up half of our positive numbers for negative numbers. All right, so let me show you the way that inside of a computer -1 is represented. All right, so like what should -1 be? It's going to be an int. It's got to be 32 bits. What does that mean? Well, if you think about it, like -1 is just a number that if you add 1 to it, right, it makes 0. So let's imagine that, and let's figure out what -1 has to be in binary. All right. Instead of 32 bits, let's pretend that our numbers are 4 bits because I cannot write that much. Let's pretend that we only have 4-bit numbers. All right. Let's try to figure out what -1 must be as a 4-bit number, and you can use the same game to figure out what it must be as a 32-bit number. All right. So whatever it is, whatever random stuff it is, whatever those 4 bits are for -1, in 4-bit land, it's the number that if you add 1 to it, right? It was just the 1 there. If you add 1 in binary to it, it produces 0. Does that make sense? That's what -1 means. It's like you add whatever that is to 1, to +1, it makes 0 because it cancels it out. So we know how to do math on binary numbers. Let's try to figure out, like starting from this bit, like what should that one be, all right? Because your hand is forced. Do you see how, if this were a 0, you would put a 1 there, and we don't want a 1 there. We want the number 0 out. So -1, the rightmost bit, cannot be a 0. It must be a 1. Does that make sense? You have to have that. And then that's going to force a carry, right? Because 1 plus 1 is 2, 1, 0, you carry. That's gonna produce the 0 there, that like we wanted. But now we have to like figure out what this one needs to be. So do you see, again, how if you put a 0 here, it would force that 1 in that position? No, we're trying to make 0. So -1 cannot have a, we still need that carry bit, cannot have a 0 here, it must be a 1 again. Does that make sense? And with the same game, like, all right, that's going to carry again 1, 0. Now what does this one have to be? For the same reason, can't be a 0 because that would force a 1 down here, so it must be a 1, carry. This one also must be a 1. And then there's also a carry out there. There's still a carry 1, but we're pretending that we only have 4-bit numbers, and so like there's no extra room for this guy. So it just gets thrown away, all right? And that works out in our favor because that produces 0. See, all 4 bits are 0. We're pretending we only have 4-bit numbers. And that means then that all 1s, 1, 1, 1, 1 in 4-bit land, that is equivalent to -1. Does that make sense? That's what we're going to do. And so in 32-bit land, it's going to be like all 1s, 32 1s for integer -1. But you kind of see the idea now, I hope. All right. Normally, this would have been what? That's the number 15. We've given up the ability of representing the number 15 to have -1 in 4 bits. All right. So we've given up some large whole numbers in 32-bit land as well to be able to represent negative numbers. So like 3 billion is not possible. Like there's like 2.5 billion-ish is the biggest whole number that you can have as an int. After that, it starts becoming negative. Okay. So yeah, that's very nice, and we gain a lot by just throwing away this last carry bit because we don't have room for it. We don't have room for it. It's perfect. We didn't want it anyway. All right, we throw away that final carry because we have a fixed number of bits to our numbers. Like we've pretended it's only 4 bits, only 32 bits. There is no 5th bit. There is no 33rd bit. Okay, so that's important. Yeah, let's do -2. Like, what should -2 be? We can play the same game. Let's say that, all right, whatever -2 is, as 4 bits again. It's the number that when you add +2 to it, that's 1, 0 in binary, right? Again, produces 0. So let's figure out what -2 has to be in binary. Well, for once, you can't put a 1 there because that would put a 1. See it? So, okay, this one has to be a 0. And then you play the same game like you did with -1. So like, okay, this one can't be a 0 because it would force a 1, so it must be a 1. Then I'm going to carry, and then for the same reason, I need 1s again. All right, and then we have another thrown away carry bit out there, and that produces 0. So 1, 1, 1, 0 in 4-bit land is equivalent. It's doing the same job as -2. Does that make sense? It's not 14 if you look at it this way. All right, it's -2. I hope that makes sense. So yeah, there is a trick though. You can find any negative number this way by playing this game, but there is a trick to get it quickly. It's called the 2's complement form of the number. That's the way that we're making our negatives inside of a computer. It's the way that works like this, where you add it and like it cancels its positive version out. It's called 2's complement, and there's a quick way to get at it. All right, this is the 2's complement representation of negative numbers, and if we want to do this quickly, to negate a number, all we have to do is flip its bits from 0s to 1s and 1s to 0s, and then add 1 to whatever we get. All right, that will turn any positive number into a negative number and vice versa. All right, so a quicker way than to get like -1 is like start with +1, flip all the bits, and add 1. It's going to work out. All right, flip all the bits. That makes every 0 becomes a 1, 1, 1, 1. Every 1 becomes a 0, just like that. And then you add 1, and so there's room in that bit for 1. And that quickly produces -1. You see it? And then it also works backwards. 1, 1, 1, 1. Let's make it the positive version of it. Let's negate it. Flip all the bits, and then add 1. Quickly we get 1. Okay? So that's what the computer's really doing. If you say negative something, like it just quickly does that. But it works as far as math is concerned, right? That's the number we want. Okay? That's going to do negative stuff if we throw away that carry bit like we will. Okay? So that's how negative numbers are stored, and now you know. And now we can talk about these bitwise operators, these things that act on individual bits of a number. All right. So the first operator, they will correspond to the logical operators that we know. If you remember those, we had like and, or, and not, right? So there's a bitwise and. Okay. There's a bitwise and inside of C++. And it is, like the logical and was 2 ampersands. The bitwise and is just a single ampersand. All right, so sorry this is overloaded. We know that it does pointer stuff, reference stuff. It also does bitwise stuff. That was the original one, though. So let's talk about that. I guess that and like address of. So yeah, the single ampersand is overloaded, and I'm so sorry. So yeah, let's talk about what it's doing, the bitwise and. Okay, it's a way to extract and see if a bit of your number, like this bit right here, was a 1 or a 0. That's what AND will give to you. And let me try to motivate, like, why would you want that? Why would you want to, like, I want to check just this bit right here. I want to know if that's a 1 or a 0. It's useful for, like, storing things in a memory constrained environment. All right. So if you think about it, like, it's nice to store things other than numbers inside of ints for that reason. You can pack them all together very tightly, because what is an int but 32 ones and zeros, right? And 1 and 0 is like true and false. So you can store 32 bools essentially inside of an int, and they're all packed together, and that saves a lot of space. All right, so like you can have a number that represents like maybe the world in your video game that you're building. All right, so like you can store as just an int 32 bits. You got 32 ones and zeros, and maybe you can use this bit to know if like your character has an extra life, and then you can use like this bit to know if your character is currently riding a horse or something, like in Zelda. You see, like you can pack things together very tightly, and that's super nice. A bool variable would take up a full bit, even though it's only going to store 1 and 0, or it's going to take up a full byte for weird reasons. But you can pack it very closely together, all these bools together in an int. All right, that's super nice. You save space. That's useful. All right. You can also like split up in it. Like I want to use just the first 4 bits for a certain number, and then the rest of the bits for another number. Like you're saving a whole lot of space that way by like not having to duplicate memory. All right, just use the pieces that you need and hook it all together. Okay, so there's a way. This bitwise AND is going to be a way to get out pieces of our numbers, get out individual bits. All right, and that's what bitwise operations mean. All right, there's a way to like get the 12th bit, set the 3rd bit to 1, and stuff like that. All right, so yeah, bitwise AND, finally, this ampersand, lets you perform Boolean AND on each bit of a number when you line up 2 numbers. All right, so I still haven't showed you anything about this. I need to just explain it first. Give me a second. All right, I just got to read these words, and then I'll give you an example. So bitwise AND, it does Boolean AND on each bit of a number, where we consider 1 to be true and 0 to be false, and it's this ampersand operator. All right, so sorry that's overloaded. In addition to address of and reference, this means bitwise AND sometimes too, but you'll know from context. All right, it's good for extracting bits, and now I can show you an example. All right, so bitwise AND, you give it 2 numbers. All right, you say like I got this number. Let's think about it in binary form, but you'll store it as just a normal int variable, for example. Let's say you got this binary number, and then you can AND it with some other binary number. All right, and that's what bitwise AND does for you. Let's see, is there anything I want to show you yet? Not quite. Yeah, let's go through this example first. And what it does, bitwise AND, is it aligns each of those numbers by their bits, because they're always going to be the same. Like you always have like 32 bits as an int. It will line them all up, and it will consider 1 to be 0 and 1 to be true, and 0 to be false. And then it does Boolean AND on those things. So like the first thing it's going to do, and then it produces another number. Okay, so what it will do is like to fill in this bit, it's trying to make a brand new number with bitwise AND. You're ANDing 2 numbers together to make a 3rd. It's going to figure out like it's going to try and ask the question like what goes here, what bit goes here for my resulting number. What it will do is it will do logical AND on these bits. So the 1 means true, and the 0 means false. So it's essentially going to do true AND with false. Remember the truth table for AND? That produces false, and so the number that it's building, it'll put a 0 there. Does that make sense? It's a little weird. Ask me questions until you get it, but that's what it's going to do for every lined up bits. All right, so then these guys, 1 ANDed with 1, true ANDed with true, that's true. False anywhere though makes false. It's going to produce 0, 0, 1, 0 out of those original numbers. Does that make sense? It's very odd. And it does not really make any sense mathematically either. So like, what was this number? This was, well, it's 15 minus, what, 4? So I guess it's 11. It's 11. We just ANDed 11 with, what is that? 6? 4 plus 2, 6. And it produced 2. All right, it makes no sense mathematically, but bitwise makes sense. That's what it's doing. It's working on individual bits, lining them up, producing a 3rd number. Okay, so what bitwise AND is good for is for extracting. It's good at getting a bit out and seeing if it was a 1 or a 0. Okay, that's what bitwise AND is good for. Let me prove that to you. So let's say that we've got a number. You're not sure about the individual bits. You could like print it out and like do the math yourself if you want, but like in memory, you can't really access a bit without doing something first. And here's the thing you do. All right, let's say you've got this number, and you want to extract, let's say this bit. I want to know, is that a 1 or a 0 inside of my variable? All right. There's also there's a numbering system to bits, by the way. This is bit number 0, the rightmost one. Bit number 0. Then it goes, this is bit number 1. This is bit number 2. This is bit number 3. It starts from the least significant bit, working its way that way. So this is now bit number 3 that I want to ask the question, like, is it a 1 or is it a 0? What is bit 3? Is it on or off? All right. And what you do to figure that out would be to AND with a number that's a 0 where you don't care. Like, I don't care about any of these bits. I just want to know if this bit is a 1 or a 0. So what you do is you AND with the number with just the third bit set. All right, that's the number with just the third bit set. That's the number, what, 8? But you can figure that out yourself. I'll show you how. That's the number with the third bit set only. Okay, and watch what happens. Everywhere you didn't care, like the false made it false, so there was zeros everywhere. But if it just so happened to be a 1 right there, that one would preserve it and keep it a 1. Do you see that? It would keep it the 1. And then you have a non-zero number, because if that was a 0, everywhere else it was a 0, it would force a 0 down here, even though there was the 1 there. Do you see how, using that as what you AND with, it will either produce a number that is all zeros, the number 0, if that one wasn't set, or the number something else other than 0, right? Or the same number back again, essentially, if it was set. Do you see it? So that's, what did we just do? We did 11 ANDed with 8, and it produced 8. Okay? That's what we just did. And so what you can do in like an if statement is check, like, okay, when you AND with this number to see if it was set or not, just check if the result wasn't 0. If it wasn't 0, then it was set, that bit that you cared about. Does that make sense? That's what it does. Okay, that's how you check if a bit was set. So here, let me show that to you. So we'll do like cout 11. That was the first one. 11 ANDed with 6. That was the first one. And then the other one was 11 ANDed with 8, right? So let's watch those work together. Whee! So yeah, the first one resulted in 2. Again, not mathematical, but bitwise. Then the other one resulted in 8. And the fact that this wasn't 0, this gave back something other than 0, that means that that bit was set that we cared about, because the result wasn't 0. Bit 3 was set. All right? And yeah, so the bit numbering start at 0 all the way up to, for an int, it goes up to 31, right? Because it starts at 0. So yeah, bitwise AND is good for extracting a bit. Next is bitwise OR. You can imagine AND implies the existence of OR. Just like the bitwise AND, like the logical was 2 ampersands, bitwise OR was 2 pipe characters, logical OR is just going to drop one of them and just say that, okay? So what it will do is it will logical OR together every bit of a number, all right? And so remember the truth table for OR. It's true if anything's true. So here's an example. It's like 1, 0, 0, 1, bitwise ORed with 1, 1, 0, 0, let's say. What will it produce? Well, again, it will line up those numbers on the bits. And 1 is true, 0 is false. It will do logical OR on those. So like, that's true, ORed with false for the 0, right? And as long as anything's true, the answer's true. So that will result in the number 1 there. The bit 1 goes there. False ORed with false is the only way to make false. And then if there's a 1 anywhere at all, it produces that. Does that make sense? So that's the number that will produce. It works on the bits. It has nothing to do with math. So what did we really just do? This was 8, 9, 9 decimal, ORed with 8, 12, 12 decimal, and it resulted in 13. So again, no math involved here. It's not real math. It's working on bits, okay? So use it for your video game when you're packing stuff together, holding a bunch of bool values, all right? So that is interesting, though. That's what it's doing. So bitwise AND was good for extracting a bit, seeing if it was set or not, like it was 0 or wasn't 0. That means it was set or not set. And then bitwise OR is good for setting a bit, all right? Because you can just like OR with a truth value there and like preserve everything. Just like you OR with a number with the 1 in the location you want to set. So here's that example. Let's say I've got my number, and I just want to make sure that the 0th bit was set, because this is bit 0, bit 1, bit 2, bit 3. Let's say I want to make sure I want to produce the number that's the same as this one, but with this bit set to a 1 if it isn't already set already. All right. So what we do is we OR with a number, that's an OR, not a 1, with just that bit that we care about set. All right. Put a 0 everywhere else. We just want to preserve, because watch what happens. This is the number, right, with the 0th bit set only. It's the number we care about setting. 0th bit set only. It's really the number 1, right? And you see how the true of that 1 is going to force a 1 there no matter what. And then all these zeros will just take whatever the other things were. Because like if they were a 1, we got a 1. If they were zeros though, then it will just keep the 0. See that? It preserves all these guys, and then it forces this guy to be a 1 if it wasn't already. Okay? That's what it does. I will make sure that bit is set in that location. So what did we really just do in terms of numbers? Even though it doesn't make sense to think of it in terms of numbers. That was 810, 10 decimal, ORed with 1. And that produced, this time it actually did kind of add it, produced 11. But you can't bank on that, right? It doesn't do math, it does bitwise stuff. So let's show some of that. Does AND stuff. OR stuff looks like this. Well, what were my examples? It was 9 and 12. 9 ORed with 12, and then we also did 10 ORed with 1. And it produced 13 and 11. All right, and yeah, this one at least, that one was the useful one. That one made sure that the bit 0 was set. Makes sure that bit, the 0th bit was set. It's going to make sure that the result has that 0th bit set. Even if it already is set, it'll just preserve it. That's fine. Okay, then it wouldn't change the number. So that's what bitwise OR, good for setting bits. Bitwise AND was good for extracting bits. They're like polar opposites. They're wonderful. And what's the other one that you remember, right? The logical operator? There was a NOT, wasn't there? There is a bitwise NOT. It's also called complement because it's going to flip things. We only had one character to mean logical NOT. That was that exclamation point. So there's no like chopping that off. We've chosen a different character. All right, bitwise NOT or bitwise complement is going to just flip all the bits of a single number. This time it only takes one number, and it's the tilde character. All right, it's a tilde character, and here's an example of that. So like tilde on this number 1001, pretending that there's only 4 bits, will produce a number with all those bits flipped. Like this 1 becomes a 0, this 0 becomes a 1, and then 1, and then 0. You see it? So like if you had 4 bits, for example, this would be 9, right? You're trying to flip all the bits of 9 in 4-bit land. That becomes 6, all right? 6 in decimal. That's what bitwise NOT does. It flips all the bits of a number, all right? And remember, though, that normal ints, they're not just 4 bits. It's going to make a giant number, which is really going to end up negative. So remember that if you flip all the bits of these guys, it's not just like you're flipping 1001. If it's an int, it's really a bunch of zeros, right? If it's the number 9, just a bunch of zeros to pad it up to 32 bits. And then it's 1001 at the end. So really, if you're flipping it, you're making a lot of things 1 secretly if it's an int. You see that? That's important. Looks like I need to do a makefile as well. So let's do a makefile just to remind ourselves that that is working and we know how to do it, even though it's just one file. So I got this bitwise.cpp file. Let's make a makefile to compile it. So it's just, I want to call the thing bitwise, right? And all it needs is that bitwise.cpp. And because there's no like separate files, I don't have to do the dash C to do the separate compilation because it's just one thing. We can just immediately say, all right, g++ on bitwise.cpp. It's just the one thing, dash o bitwise. All right, so that's my makefile. Now I can say make bitwise to quickly make it. Alternatively, I can just, even faster, I can just say make because it will run the first rule of the file and then it will make it if it needs to be remade. All right, this time it's already been recompiled. So there. With that, let's have some examples of bitwise negation, bitwise not. Oops. Let's do cout. Let's do that first one first. That was tilde9, right? Tilde9. What was that result? It's going to put a lot of ones. It's really a big number, right? It's a big, big number. 11111, then it ends in 0110, right? So like, what does that end up as? So let's remake it now and rerun it. It produces -10. All right, so it's such a big number that it wrapped around and became one of the negative numbers that we know. All right, so we've given up a number like that, a number so large, after all flipping all those guys, to be a negative number. All right, and that actually leads into the idea of negating. Right, if you want to negate a number, what's going on under the hood is it's doing that 2's complement form. It's flipping all the bits and adding 1. Do you see how that's why we were 1 off from the -9? So we flipped all the bits. We just forgot to add 1, so that's 1 away. It's 1 away from -9. Do you see it? So let's make a function that does just that. It's like the long way to negate a number. Let's make negate 2's complement. So it's a function that'll take a number and negate it for us. So let's, I don't know, want to call it like this, negate 2's complement on 9, and then it will do the negation and produce -9. So let's make that function. So it will take an int, and it will return the negative version of that int, having done the 2's complement way of doing it. So I return -n using 2's complement. So what do you do to make 2's complement to your original number? You flip all the bits and then add 1. So you return not just tilde-n, that only flips all the bits. That's called 1's complement for a weird reason, by the way. To make it 2's complement, we add 1. All right, that's our final result. And that'll do it. Boop. So there's my -9. So I gave it 9, +9. Oops. I gave it +9, and then it took it and flipped all the bits and added 1. So it made -9. First -10, then added 1 to make -9. Okay? So that's what's going on under the hood when you do negation. Like in the processor, it can do all that at once, but now we're seeing what's really happening. All right? That's what negation is good for. That's how it works. That's one reason you might want to flip the bits of a number. All right? So there's that. What else? What else? Yeah, I just want you to try now, I think. Here is some code. Right, here's the code that was doing stuff for the ands and for the ors. Remember those? And I'll go to the slide in a second, so if you want to pause there too. But here's some questions for you. I'd like you to write some code that unsets the 5th bit of a number named x. So you've got a number called x. Somebody's already set it. Int x equals something. And then you need to unset the 5th bit of that number. All right? So like, let's say that this is the number. 1, 1, 1. With zeros on the left. 0, 1, 0, 1, 1, like it's an int. And what's bit number 5, first of all? This is bit 0, 1, 2, 3, 4, 5. And then that means this is the one I want to unset. Make sure it's a 0. You see it? That's what I'd like to do. And so that needs to turn into a 0. And everybody else needs to stay how they were. All right. So there is a way to do it in one line. Like you could fill in this, but there's a longer way as well, like x equals blank. There is a way to do it in one line. Don't worry about that right now. Here's what I want you to think about, all right? So I want you to set the bit 5 to a 0 no matter what. I've shown you not, which flips things. I've shown you bitwise or, which sets a bit, makes sure a bit is set. And then bitwise and extracts things, all right? It gets things out. It can also force a 0 if you want. So I claim that you can do this unsetting the 5th bit with a not together with an and. All right, the not was this one, and the and was this one. Just think about it, all right? And here's your other hint. Extract every bit except for bit 5. Do you see how that turns into an and? So here's and, slide. Look at that. And then here's what bitwise not was again. So flip between those two and see if you can write some code to flip, right? Or sorry, not flip, but unset the 5th bit. Extract every bit except for it. Did you get it? So yeah, let's see. Let's see. You can do it with like you can do it in a single line. Let's think about it. Like you need to do a not and an and. Why? So let's say that this is my original number. I want to unset the 5th bit. It was 1, 1, 1, 0, 1, 0, 1, 1. That was bits 0, 1, 2, 3, 4. There's 5. So that's the bit I care about. Unsetting. I want to and it with what? All right, to unset every, sorry, to extract every bit extraction is and. So I want to extract every bit except for bit 5. That means like preserve everybody else, give a 1 here, right, for preserving. But I don't want to extract bit 5. I want to force a 0, so anding with false will do that. Do you see that? So this is, I'm anding with this number, with 1s everywhere except for the bit that I want to set. Do you see how that's going to involve a not? And really this is intland, so like originally this number was a bunch of zeros, right, padded to 32 bits. And then this one has a 1 everywhere but this bit. This is the one I want to mess up. I want to preserve everybody else, so put a 1 everywhere I want to keep. So like everywhere there was a 0, there's now a 1. You see that? That's what I want. So do you see how, first of all, that would produce the number I care about? It would preserve everybody, the trues and the falses, would preserve whatever was already there by just putting a 1 there. Everybody else is preserved. And then the 0 forces a false, right? Anding with false anywhere forces a false right there, even if it wasn't already false, like it wasn't here. Do you see how that's the number you want right there? I just want to like and with this weird looking number with a 1 everywhere but that bit. How could you obtain that number? All right, it's a weird looking number. How would you calculate it? Do you see how an easier way to get it is just like, all right, start with a number that's only a 1 there. Does that make sense? Like 0 everywhere, but a 1 right there in the 5th bit. Let me count this right there. 1, 2, 3, 4, 5. Yeah, that's it. That's bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, and then zeros everywhere else. So just a number just like that with a 1 right there. Do you see how if you flipped all those bits, it would turn into this one you want to and with? That's the secret. And so that's tilde on what? 0, 1, 2, 4, 8, 16. It's number 32. Tilde 32 would give you the weird looking number. Apparently like what? Negative 33 or something? Something like that. That's the number you want to and with. Does that make sense? Like x becomes x anded with tilde 32. That would force this bit to be unset to a 0 and preserve everybody else. All right? Ask me lots of questions about this one, or pat yourself on the back if you got it, because that is a fun example that's just making sure you understand things. All right, so let me show that to you. That's crazy, right? So, new line, and then it was... I guess, honestly, I don't really need to show it to you. You see what's happening. Like, the number parts don't make sense anyway. So I think I'll just keep it like that, sorry. Yeah, keep it on the slide. Go to code if you want, though. See what number that really was. Yeah, let's next go to one more, like, main logical kind of operation. Then we'll talk about a couple more bitwise operations after that. So this is the last kind of logical operation. It's called exclusive OR. So it's kind of like OR, but not really. So exclusive OR is short for bitwise exclusive OR, all right? XOR, I say for that, right? We say exclusive OR and XOR for short, okay? And here's the difference. It is a binary operation, or sorry, it is a logical operation. There's a regular OR, the one that we know, right? Regular OR. I'll show you that one, and I'll show you what the difference is. Regular OR, and then there's also exclusive OR. So I haven't shown you the logical exclusive OR yet, but now's the time for that too. So here is regular OR. You've got X, you've got Y, and then we do X ORed with normal ORed with Y. All right, that's going to be what? True, 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 false. All the possibilities, right? False, true, false, false. And then just to save me time, let me copy and paste that before I filled everything in. So I want to do the same for exclusive OR, and that's XOR. So I'll just put an X right there. Show you the difference. All right, so normal OR is just like, it's true if anybody's true, ever. True, the only way it's false is if both are false. And that is still true down here. It's like exclusive OR, like it's false if both are false. It's true if any of those guys are true. But the one place that it differs is it puts a false right there. It needs to be exclusively true. All right, that's what the difference is. So if they're both true, exclusive OR says no. No, I'm saying false there. It's only true if one or the other is true. All right, not both. Does that make sense? It's exclusively true. All right, so yeah, regular OR gives back true when one or both sides are true. So like if anybody's true, it's called inclusive OR for that reason. Exclusive OR is true only if one of the sides is true. It's exclusively true. All right. There is technically a binary operation or a Boolean operation for exclusive OR. It's the not equals to. on trues and falses, isn't it? It's like it's true if it's not equal. Does that make sense? But for exclusive OR, it's this character. It's for bitwise exclusive OR. It's this caret character, and now you know. You probably tried this and you thought it meant power. It is not doing anything power operation like. It is doing weird bitwise stuff. All right, so that's why you got a weird answer if you ever thought that that meant power. Okay, so it's exclusive OR, bitwise exclusive OR. And so with that in mind, here's an example of bitwise exclusive OR. So like that one exclusive OR'd with this one. What does it do? Well, it lines them up again. It's like, all right, true exclusive OR with true. Well, that's false. Can only be true exclusively. All right, so that's the false case. And then these guys, they differ. So it's a 1. And then this one also differs. Does that make sense? So that's bitwise exclusive OR. Let's show that in code. So that was, what was this, by the way? This was, that was 11 again, right? 11. Bitwise exclusive OR with 5. And what did we get out of the deal? We got 14 somehow. It's a little weird. All right, so not normal number stuff, but bitwise stuff. So let's do that. So that was 11 exclusive OR with 5. Now finally you know what that character does. Okay, there's my 14 out of the deal. And yeah, exclusive OR is useful when you get to like a CSCI 45 kind of class where you learn how to build a CPU, because like exclusive OR will do almost addition for you. It's mostly addition. It is kind of like addition on single bits at least. Do you see that? It's like you can build circuitry to make addition on like 32-bit numbers using a bunch of exclusive OR things. All right, one day. All right, one day we'll get that. So here's proof of that. Like 0 plus 0, that's 0, right? That's the same as exclusive OR. 0 plus 1 on a single bit, that's 1, right? Same as exclusive OR. 1 plus 0, same deal, right? They're different. Exclusive OR said that that was, or sorry, exclusive OR said that that was a 1, either one. And then 1 plus 1, what is that on a single bit? Well, you got to carry, but like it's 1, 0, and so there's a 0 in that place at least. And again, exclusive OR was doing the right thing. Interesting, right? So exclusive OR is kind of like addition, and you'll see that pop up again in a future class. Okay? But yeah, we'll get to that. We'll get to use of exclusive OR soon. But like I said before, I think, or maybe I never said it, but and or and not are kind of all you need. You can create exclusive OR using a combination of and or and not. So you don't really need to know it, but it is useful to know. All right. Here's a great operation though. It's very, very useful to know. Otherwise, it would get very, very tedious. It's called bitwise shifting. So these original operators that we were using for like cout and cin, they really came from bitwise land in the C language, and we get to use them still on numbers like that. So there's bitwise shift operations. This is left shift, it's like a left arrow. This is right shift, it's like a right arrow. And what the shifting does is it like moves bits over. Every single bit moves over, all right? So left shift is going to shift all the bits to the left and bring in fresh zeros, all right? So for example, let's say that we start with this number, and we want to left shift it by 2 bits. What that will do is it starts with that number again, and then it shifts it to the left. It moves it over one, so that like it brings in a new slot, and then it moves over again. We're doing it twice by 2 bits, and each of those new bits gets filled in with a 0. If there was stuff over here, they get chopped off because we had to make room for the new bits, but usually they were zeros, and that's what happens. Does that make sense? That's what left shift does, and by adding zeros to the end of a number, it's multiplying it by a power of 2 actually, which is kind of cool to think about. Watch this, because what is this? This is the number 11 again, right? This is 11 in decimal. What is this number? This is the 1's place, the 2's place, 4's, 8's, 16's, 32's place. It's 32 plus 8, so that's 40. 44. It just multiplied it by 4. Does that make sense? That's weird. So in general, if you take a number and you left shift it by a certain number of bits, it will create the same as that number times 2 to the ith power. You shift it once, it just multiplies it by 2. It's like, for example, if you start with 3, here's the number 3. If you left shift that by 1 bit, then it will keep that number, keep the 3, bring in a new bit, right? Because it's moving them over. Bring in a 0, and what is that? That is suddenly 6, right? This is 6, which is the same as 3 times 2 to the first power. And then this was 11 times 2 to the 2 squared. So it's just like every time you shift by a bit, you multiply by a power of 2. You shift by more bits, you've multiplied by a bigger power of 2. That's kind of neat, all right? A fun fact is that inside of older computers, it was faster to do bitwise operations than to do multiplication. And so if you ever did like 3 times 2 or 11 times 4 inside of a computer back in the day, the compiler would turn that into, because it was like you're multiplying by a power of 2, it would turn it into the appropriate left shift because that was faster for the processor to do. And so you get speed out of your program. The compiler just noticed that and did it for you. That's really cool. Okay, so that's the thing. And yeah, just like there's a left shift, there's a right shift, and it does exactly what you would expect. It's going to shift bits to the right and chop off things from the right side because of that. So like if you start with this number, like 101, remember really, it looks like this. It's like padded with zeros. That's the number 5, right? Padded with zeros. If you right shift that by 1, it's going to like move things that way and bring something in new over there, which means it's getting rid of this bit. Does that make sense? Bringing in new stuff over here. All right, so it turns into then, like you got all the original stuff, 0, 0, 0, 0, 0, 1, 0, 1, 0, and you chopped off that one to make room for this guy because you moved them all over, right, to the right. So it turns into that, okay? And then this gets filled in with a 0 usually, okay? And yeah, it's going to divide. It divides by a power of 2, essentially. So this was 5, this turned into 2, it did integer division. This is 5 divided by 2 to the first power because we right shifted by 1. So that equals 2. So yeah, that's what right shift does. It divides by a power of 2, more or less. It chops things off, if you want to think about it that way. Though, I should say that when you do right shift on integers, it won't always bring in a 0. Left shift always brings in a 0. Right shift only brings in a 0 if the number was positive. So, or 0. It brings in like whatever this bit used to be, essentially. Like if this bit, this leftmost bit was a 0, it'll bring in a 0. But if this leftmost bit was a 1, then it will bring in a 1. All right. The reason that is true is because we use the leftmost bit in integer land to mean if it's positive or negative. If it's a 1, that's a negative number. If it's a 0, it's a positive number. And so it's going to keep it positive or negative by bringing in that proper value. All right. So don't worry too much about that. You'll learn more about that in a future class, but like it's going to bring in something different. It's going to do arithmetic right shift. That's the word. If you had an unsigned int that could never be negative, then it is always going to bring in a 0. All right. Either way, it's going to divide by a power of 2. Okay. So that's what shifting does for you. And let me show that to you. We did a left shift. This was 11 left shifted by 2 made 44 multiplied by 2 squared. So let's do that one. It was 11 left shifted by 2. And then this one, the next one was 5, right? 5 right shifted by 1. And that turns into 44, multiply it by 4. And this one divided by 2 integer division. So that made 2, because it was 2.5, right? That's what shifting is good for. And let's see. Now you have the ultimate package. Now you can build numbers like this weird 32. You didn't have to know that it was 32. You can build, like when you're doing and or, like I want to or with a number with the 0th bit set. I want to and with a number with the 3rd bit set. Now with shifting, your life has become so easy. Here's how you do it. All right. So notice, like let's say that I want to set the 3rd bit of a number. Then you or, right? You or to set. What is the number that you or with? Like let's say you got this number and you want to make sure the 3rd bit is set. 0, 1, 2, 3. There's your 3rd bit. You want to make sure that's set. You or with this number, right? The special number with only the 3rd bit set to produce this. What is this number? How do you calculate that number? It is the number 8, but you don't need to know that. Because you could start with the number 1 and then just bring in those 3 things, those 3 zeros, by left shifting it by those bits. Does that make sense? That's the secret. That will build this number for you quickly. You don't have to know that it's 8. It's just, this is the number with the 3rd bit set. Is that not magical? That's beautiful. And then if you want to get out, you want to extract, right? You do and for extraction. You want to extract the 3rd bit. You and by that number with just the 3rd bit set. So like you got this number, 0011 again. You want to know, like, hey, is this bit set, right? Is this bit set to a 1 or not? So you AND with a number with just that bit set, and then it will either be, like it gets a 0 everywhere else. If that number was a 1, it will put a 1 down there. But if it was a 0, it makes the whole answer 0. And like, how do you get this special number with just the third bit set? A quick way, you don't have to do any math. It's like start with 1, shift it left by 3. Is that not beautiful? That is lovely. Okay, I think that's wonderful. And so instead of what we were doing up here, like we did in, this was the AND, right? We did this AND to extract the third bit. Boop, just like that. Let me show you the cleaner way to do that. We did that one, and then what was the other one? We did an OR, right? To make sure that to set a bit, like all right, it was a special number 1. Here's like the cleaner way to do that. So if I want to make sure that, or if I want to check if bit 3 was set, I want to AND with the number with just bit 3 set. That's 1 left shifted by 3. That's it. Does that make sense? That's the answer. And then same with this one. I want to OR and make sure that the 0th bit was set. Like if you didn't know that was just 1, you could do like, all right, start with 1, left shifted by 0. That'll make sure I got a number with just the 0th bit set. All right. I guess this one you could have hard coded, but you see the usefulness of this, right? And so you get the same answers, but like it was much simpler to do that calculation. Like, okay, yeah, it was non-zero, so it was set. Okay, there, the bit 0 was set. It changed the number because that bit wasn't already set. I hope you see it. All right, that's super cool stuff. So with that in mind, I've shown you a bunch of bitwise operations. I just want to give you some practice to make sure you're understanding everything. So here's a question for you. Please try to write some code that not sets, not unsets, but toggles, does both. Toggles the 4th bit of a number called x. All right, so you've got, again, somebody gave you a number, int x, something. See if you can toggle it. That means set it to a 1 or a 0, depending. All right, so let's say here's my example, like 1, 0, 1, 0, 1, 0, with a bunch of zeros on the left again, padded. What's bit 4? This is bit 0, 1, 2, 3, 4. So this is bit 4. You should make some code that either, like you run it either way, like you make it a function that toggles it. So if it's a 0, it makes it a 1. And then it preserves everything else. Preserve everybody else. But also your code should have worked if this was a 1. It will toggle it back, that 4th bit, back to a 0. Does that make sense? So your code somehow should notice, maybe with an if statement that would work, to do it, right? If this bit is set, if this bit is unset, make it set. If it is set, make it unset. You know how to do all those pieces, right? You could do it as a big long if statement, but there's also a way to do it in one line. All right, so let me flip through all the examples. There's AND, there's OR. You might need any of these, right? There's NOT. There was that example, that unset stuff. There was exclusive OR, and then there was shifting, and now shifting is helpful for getting a certain number that we care about. And now here's your question again. All right, so give that a try. It's very, very useful to try it. See if you can get it. All right, I do claim that there is a way. There's a way to do it in one line again. I'll show you that way too. But the way that you know how for sure, without any extra thought, is like this, right? You could say, all right, if the 4th bit is not set, if bit 4 is not set, then what does that mean? It's not set if taking it and ANDing it, let's see, if taking it and ANDing it with just a number with a bit 4 set, right? 1 left shifted by 4. If that is equal to 0, then it's unset. Does that make sense? Like this is making sure, this is checking and seeing, is bit 4 unset or not? It's unset if the AND makes a 0 there. All right, so that means it was unset. Set it. So you can use an OR, right, to do the setting, the OR operation. That's OR. Else, if you're in the else case, then you know that it was set. That means, all right, this was false. That means it wasn't 0. That means it really was set. Then you want to unset it. And you know how to do that from this example here, right? It's going to be a not and an and in some order. You're going to do an and with some negated thing. Okay, that's that one. But there is a trick. notice how you're toggling things. Let me show that to you. There is a way to do it in one line with a certain operation. There's one that toggles stuff. Do you remember which one? Or makes sure it's set and checks if it's set. It unsets things easily as well. Exclusive OR. Exclusive OR is going to do a toggling feature because of this fact, because of this weird thing that's different to normal OR. It will toggle for you. So here's the answer. So like if it was unset or if it was set, you could exclusive OR with a number with a 1 just there. The zeros would correctly preserve everything because if they're different, right, it produces a 1, produces a 1. If they're the same, it produces a 0, 0, 1, 0. So preserved everything. And then this guy, do you see that it will toggle it now? Because 0 and 1, they're different, so it makes a 1. It just got changed. And then if it was a 1 already, with that same number, exclusive ORing with just a 1 right there, oops, yeah, and a 0 everywhere else, then again it would preserve everything, like they're different, so 1, different, same, different, same, and then it would again toggle this one because now they're the same. 1 and 1 makes 0. Ooh, that's another reason to know exclusive OR. Does that make sense? So you're going to take your number the quick way and exclusive OR it with the number that has just the 4th bit set, just the 4th bit set. And that very easily you can get with, start with a bit with 0th bit set, shift it over 4 bits. That makes sure that the bit number 4 is set. You can see that? That's the answer. That's the quicker answer. But I know that you could do it this way, all right? So make sure you can do it that way too. Because in a pinch, if I ask you something weird, you can always get at it with this kind of way, with ands and ors and nots, all right? Don't have to look for something fancy all the time. So yeah, that's a fun little example, I think. I hope you see it, and I hope it makes sense. Please yell at me if you have any questions about it. It may not be very obvious right now why you should care about any of this. So I do want to kind of motivate it again. Packing stuff together tightly, as holding a bunch of bools, that is very important when you have like space considerations. But maybe you're like, I'm always going to be working on large supercomputers. We're going to have plenty of memory. I don't want to be a low-level software engineer. I don't care about bitwise operations. You still should care. Here are some other reasons why you might need bitwise stuff. All right. So one fun one, and you will be forced to take a compiler class usually once you transfer to a 4-year college. If you make your own compiler, you have to generate machine code. And machine code is just 1s and 0s. It's binary numbers that represent instructions. All right. And those numbers look weird. They have special bit patterns. Let me show that to you. So let me take my bitwise program. You know, you've probably tried this, right? If you open up the executable file in Vim, it is disgusting, or even in Nano. This is unprintable stuff. It's not an actual program, all right? Or sorry, it is an actual program. It's not text. It is binary. It's a binary representation that the CPU can understand, not humans, all right? There's a way to unwind that. There's a program called objdump, which is short for object dump. And I say -D for decompile. It was compiled, uncompile it, decompile it, and they give bitwise. And it's going to spit out the decompiled form of everything. And then if I look at it in another program, these are the CPU instructions that correspond to my bitwise program. All right, there's the main function eventually. Let me search for that. Where's the main function? So here's the main function. Here's where it starts, and it's doing weird stuff. All right, so these are called assembly instructions. Those are still just text for humans to read. It's like push this, move this special place in the CPU to this special place, move the number 2 into this special place in the CPU. And there are there's a binary encoding of these operations, all right? It's in hexadecimal actually, because binary would take too long. It's like this push operation, whatever that does, it's hexadecimal 55. This move operation, to move this place into this place, is apparently 3 bytes. It's 4889E5. This other move, doing other things. But do you see how, like, all right, this move that moves this guy into this guy looks like this, and this other move that moves a different place into another different place looks like this? It's very similar. It still starts with 4889. You can make a number, right? These are really just numbers that correspond to these instructions, and that's what you're putting into this output file. That's what a compiler does. That's its job, to generate these weird-looking numbers that correspond to these assembly instructions that the CPU can understand, right? It's okay if you don't fully understand this, but like that's what the compiler's job is, to make it something that the CPU can understand, which is really just 1s and 0s. And you see how, like, if you're the compiler, like, you need to make this move operation inside the CPU happen, well, you know to make a number that starts with 4889, and then you swap out that last byte with like whatever corresponds to these two things. Like apparently E5 corresponded to these two things, and C7 corresponded to these two things. It was different. And so you'd swap it out. You'd unset those pieces. You'd OR in the things that you needed, right, to set the proper bits. Does that make sense? Like, that's one really good reason to care, all right? You have some weird bit patterns that you need to create to just make code that runs on a CPU. And like that is your job now, all right? That's important. And then also, if you're working on anything like that has to do with compression, so image files, for example, are stored in a binary way. They're stored in a compressed binary way, and it doesn't look like text at all. It's, again, something for like a low-level program to unpack and understand, and it's trying to be efficient in space. All right, so like image files, you have to go to certain bits of an image file, right? Because if you look up an image file in like an editor, it's still not text, right? It's just a bunch of binary. Image files, like they're storing in some bits, like the size goes at these bits, the colors go at these bits, and then it's RGB, a bunch of byte values. If you want to extract byte values, you need bitwise operations. If you want to change an image, if you want to make a program that looks at an image and displays it on the screen, like somebody is doing bitwise stuff somewhere, and that could be you, all right? So I hope that makes at least a little bit of sense and helps to motivate these things. It's worth learning. I can really only show them to you in terms of numbers right now, because like it's very hard to make a compiler. That's going to be an upper division class, but like this is possible, all right? These are reasons people know these things, and you should know them too, all right? So I think that's where I want to stop. That's bitwise operations in a nutshell. Do study this. Do yell at me if you have any questions. But that is where I want to stop for this set of slides for now, where there is more to them. There's a completely different topic, but we'll deal with that next time. All right, so I'll see you then.